Right, yeah, so hi, so I'm David, and today I'm going to tell you about some recent advances on quantum LDPC codes, and which includes these quantum locally testable codes and codes with transversal gates. And so this is based on a joint work with Irit, Thomas, and Louis. Yeah. So I know that not everyone is a quantum physicist, so I'll just start by giving a very quick review of like what quantum code is. So if you first think about quantum code, you might think, okay, it's about encoding k qubits into n qubits, similar to a classical codes. But turns out this description is very hard to work with. So if you look at the literature, they would just tell you in a different language. And so instead, people work with these parity-check matrices. So in particular, here we'll have two parity-check matrices, HX and HZ, and we'll think of them as like linear maps from F2 to the N to F2 to the MX and MZ. So here, MX and MZ, they're like the number of X check and Z check. So in particular, the HX, it would detect the Z error, and HZ, it would detect the X error. Yeah, so X error is just like the usual bit flip, so flipping between 0 and 1. But the Z error is like a funny quantum error, so it's like a phase flip. So that changed the plus sign to the minus sign. So these parity-check matrices, they have to satisfy a condition where like so HX transpose times HZ, it has to be equal to 0. And so we can rewrite it into this form. So here you have 3 vector spaces and you have 2 linear maps, and they compose together. For some of you, this might look familiar. So this is exactly the chain complex. So the delta and delta compose into 0. So what I'm saying is that, so it's actually possible to study quantum mechanics without knowing anything about quantum mechanics. As far as they're concerned, it's simply a chain complex with the chosen basis. So chosen basis means that these vector spaces, there's a basis that you you choose. Okay. All right. And so quantum codes later on will be defined through these 2 parity-check matrices. And next thing we have to think about is, okay, what does this code word mean? So traditionally, a code word are exactly the image of your encoding map. But again, as I say, encoding map is hard to work with. So instead, we think of it in a different way, which is through the logical operators. So these are the operators that maps code words to code words. So in this context, they're, again, the X type and the Z type. So turns out they correspond to exactly the homology and cohomology class of your chain complex. So more explicitly, the X logical operator, they're elements inside Z1, and they're equivalent up to this B1. So Z1 and B1, these are like the kernel and image of your delta maps. Okay, and these are, both of these, they're vector spaces inside this F2 to the N. Right. The same thing also holds for the Z logical operator, but now you're mapping in the other direction. So these partial maps. So these partial maps, they're really the transpose of these delta maps. And you define it the same way. So you have the Z and F. Okay, so far, any questions?
What do you mean ecological operator but not cohomology?
That's cool. Okay. So, right. So what's going on is that like you have different quantum states. That's like the code words, but these code words, they are not bit strings. There's something in the Hilbert space. But this thing is kind of hard to describe. So generally it's described through these poly operators, which can indeed be represented as bit strings. Okay, I can say more physics afterwards. But for now, we can just think of them as like homology and cohomology classes. And so from there, we can now just define these code parameters. So we have N, K, D, and W. So N, K, D, they're fairly standard. So N is the number of physical qubits. K is the number of logical qubits. So that's also the dimension of your homology. And then you have distance. So distance is the number of poly flips that you would change from one code word to the other. So these are quantum states. And again, we can split into the X kind of poly flips and the Z type of poly flips. So turns out there are 2 types of distance. So what would be the distance for the X poly flips? So it would be something that's like a X logical operator. that's in Z. But then within it, there's this B, which actually is also a logical operator, but it doesn't change the code word. It sort of fixes the code word. So that's why we don't consider them. And we take the minimum among all the C that's inside Z, but not B. Yeah, the minimum having weight. Okay, we can do the same definition for D. And for some of you, this definition is also known as the systolic and co-systolic distance. So really many quantum questions can be rephrased in just purely classical terms. Okay, and then we have the W, which is the maximum weight among the among the check and the qubits. So in other words, it's like the number of non-zero entries for each row and column inside your parity-check matrix. In our context, we'll always care about these LDPC code. That's when this W is like constant or like polylog. And so in other words, these HX and HC, they're always sparse matrices. And so here there's already a sort of a non-trivial question, which is, does there exist quantum LDPC code with these parameters? So K being linear to N, D linear to N, and W being a constant. So these are sort of the best parameters one can hope for. And one can ask, can we achieve them? And turns out this is sort of an open question for 20 years. It was also only resolved recently in 2021.
Maybe you can go back to the previous slide.
Uh-huh.
It's a lot of definitions and maybe we don't need all of them. So
I see.
maybe
Yes.
say like in the simplest terms, like what you're looking for, if you're looking for a code with the distance and so on. I mean, basically, if you look upstairs at this two linear maps composed, you're looking for these two parity-check matrices that they're orthogonal to each other. And you say again what the distance is, that it's dx and dz.
Okay, so dx, so the C that we'll look at, these are the vectors inside this F2 to the N that would map to 0. But we remove those that they're the image of this like blue map. Okay, and for this dz, it'll be like the opposite direction. You run the same kind of definition, but in the other direction.
So you're doing something where you're like relating, I guess, quantum states to these bit strings. Saying something about this. So the bit string, but it's in the whatever in Z1 minus B1 or something. So it's like one of your logical code words. How do I convert it to like an actual state, or is that really complicated? So you kind of said you were speaking that under.
Yes, it's a bit complicated. So that's why I'm just hiding it. But I can say more afterwards.
Okay, well, the point is that like you have identified I guess the like quantum states that are in your code with these bit strings. You just do sort of normal math on like, the bit strings, and like the distance is determined purely by like the combinatorial properties of these bit strings.
Right, exactly. So because when you talk about the quantum state, sometimes it looks a bit continuous, but turns out you can sort of turn that into a completely discrete kind of combinatorial question. Okay.
Going back to the next slide. Like here you're talking about asymptotics, and I like this because I'm a theorist.
Yes.
But like you actually also care about the exact constants here. Like, should I think of W as being like 3 or like 2 to the 100?
I see. So turns out there's also kind of a weight reduction scheme. So in the classical codes, given any classical codes, you can always turn that into some code with W equals 3. So here there's some similar thing where for any quantum code, you can turn to W equals 5. So that's why, of course, your K and D would get reduced, but for today, we don't have to worry about that constant. Okay, and so later on we'll say like why this turns out to be a kind of a challenging question. But let me just say that today we'll sort of talk about at least 4 of these construction that sort of build up to the final results on this K and D being linear. Yeah, so the first construction of these quantum LDPC code was by Kitaev in 97. So that gives you like constant dimension, but square root distance. So afterwards, in the same year, this is improved to a linear dimension, but this distance is still square root. And actually, it's pretty much the same over the next 20 years. So this distance it only improves by at most a polylog factor. It was only until like 2020 where the square root barrier is broken and you really get a polynomial improvement. Yeah, and afterwards, like the floodgate is sort of open and yeah, so that's where we end up with this results that fully resolve this problem.
You need distance in both directions, right? If you just want it in one direction, is it easy?
In one direction, it's easy.
Just a regular error correcting code.
I believe, let me think about this. I believe it's easy. Okay, I'm not sure. I can think about it afterwards. Yes, but the next slide I will say like why this is not easy. Turns out.
I think even in like these simplicial complexes, the systolic distance is large, but the systolic distance is small.
Yeah. Right. Okay.
I mean, it's still not so simple.
Yeah, that one's okay.
But you could also take the hypergraph product and balance it so that one side is scaling, but still not like elementary.
Oh, okay.
Okay. Yeah. So, right. So people have studied some distance balancing tools. So one can increase one side of distance, but that would reduce the other side. So getting both sides is the challenge here.
That's sort of where square root comes from.
That's exactly
The product of the two is.
That's right. Yeah, and let me just say a few more words on why this turns out to be not so easy. So one reason is that, oops. Okay, yeah, so some of you might know a similar question in a classical setting. So in a classical setting, one can also ask, okay, I have LDPC codes and classical LDPC codes, and can I get like distance and dimension to be as large as possible? And turns out this can be done pretty straightforwardly by just taking just a sparse random parity-check matrix, and it will work. But it turns out the same doesn't hold for quantum, and one way to say that is that, okay, quantum codes have to satisfy this additional condition. And if you just take two random parity-check matrix, then when you multiply the two, it's not generally zero. And another way to say that is that, okay, like really the quantum question is sort of like it has some kind of 2D nature to it. And so we know very well on how to construct random sparse graphs, but it turns out we don't really know that well about how to construct like random 2D simplicial complex. And that's also sort of a challenge in the like high dimensional expander. So we believe that random objects should be pretty general and they should like often like saturate parameters, but we don't know how to construct them.
I guess a priori, it's not even clear that this object should exist or like a good quantum LDPC code.
That's right. Yes. But later on we'll see some examples.
I mean, since it was for a long time stuck at distance square root, then people conjectured that you cannot do any better with square.
The first problem Shachar gave me in grad school was to disprove the existence of qLDPC.
Yeah.
He knew that's wrong, he just tried to test you.
No, it's been working on it.
Yeah. So right. So it turns out it's not so easy. Right. But one can also ask, okay, why do we care about this kind of question in the first place? So one reason is like for a pretty practical reason. So in a quantum code, so it turns out quantum is very noisy. So even just like measuring the syndrome. So usually when you do error correction, what you do is you first measure the syndrome, then use that to sort of correct the error. But actually when you run a quantum code, even measuring the syndrome has some error in it. And this error sort of depends on how much qubits you look at. So that's why we want this LDPC condition, which generally have a lower syndrome error. And so that means like better code performance. So in the practical side, these are also very important. But on the theoretical side, it's also a very interesting question because that's really just the beginning of a series of other questions. So on the left, it is the quantum LDPC code that's now solved. But on the right, we have a bunch of questions in quantum. So for example, like quantum PCP, which is like very, very wide open. But between there are some intermediate questions. So one of them is these quantum locally testable codes. So in the classical setting, we know that LTC and PCP, they're somewhat related. And well, so it's believable that that we should also understand quantum LTC before tackling these questions on PCP. Yeah, but additionally, one thing to note is that in PCP, it has some kind of computation feature inside, built in inside. Whereas for codes, they're just like linear. They're just like linear properties. So what I want to say is that locally testable codes, it captures the robust aspect of PCP, but not the computation aspect. So that's why we also want to study codes that have these transversal gates. And in a classical setting, you can think of it as like a multiplicity code. So a multiplicity code is some classical codes, C1, C2, and C3. And they have this property that if you take two code words, so one from C1, one from C2, and then you sort of do an entry-wise product, you want it to be in another code, C3. And in general, this is not an easy property to satisfy. So if you just take random codes, it actually doesn't quite work. You often need to take some kind of codes with some algebraic property. And so that's also the same in these quantum LDPC codes. So these codes, they have some built-in algebraic features. Okay, and once you have these two objects, and maybe with some other stuff, one can hopefully like begin to think about these PCP problems. Okay, so that's a more theoretical motivation. Okay, right, and let me just say that, so we have made some intermediate progress on the two problems I just mentioned. So in one of the work, we showed that there exists quantum locally testable codes, which has like nearly optimal parameters. So all the parameters are optimal up to a polylog. And in another work, we have constructed these codes with these transversal gates. So here the distance is only a cubic root, so that's a bit far from the optimal value n, but it's already a big progress from some previous thing that we know. Okay, so any questions on it?
Are you going to define these transversal gates?
Yes, that would, right, we'll do that.
Is this like whatever log q soundness kind of the same thing as the distance? Like, is there sort of some trade-off you get there between distance and soundness, or?
Right, so you notice that these two have the same kind of factor, and it comes from the fact that we use sort of the same kind of proof technique. So the way we get the distance soundness is actually
So they're not
the same way.
inherently coupled.
Okay, yeah, so all right, so those are some more advanced stuff. Let's move back to the earlier question, which is how do we even just solve this question of finding good quantum LDPC codes? So in other words, like how do we find ways to satisfy this chain complex condition? So the first idea is to use topology. So in topology, we know that, so given a topology, we can sort of cellulate this complex, and then we can take the like the cellular chain complex, and well, that's a chain complex. So that would give you a code. And that's exactly the idea back in 1997 by Kitav, which gives you the Torah code. So let me go into the details. So first you take a 2D manifold, in this case a torus, and then you can cellulate this manifold, so in this case into a grid, and then we can take the cellular chain complex. So how it works is that we'll map the vertices to the edges and to the faces. Okay, so this x0 is simply like all the vertices in this picture. Okay, and these maps, they are the incidence matrices. And so just by taking a finer and finer subdivision, one can get a family of codes, and this is sort of what you will get. And here K is a constant, it's because like the homology of this chain complex is sort of just determined by the manifold. It doesn't change by how you cellulate it, so K doesn't improve.
Maybe just say, when you do this thing, why was it a good idea? You need to check that delta times delta, well, that you move from something on the vertices and you take 2 steps, you get to 0.
Okay, yeah, so let me say that like the reason it satisfies this kind of chain complex condition is that if you take a vertex and you take a face, you will see that they always share like 2 edges. Okay, and we work with F2, so that means you compose, these two maps would compose to 0. Yeah. Okay. So that's one way to construct these chain complex. But now we want to improve these code parameters. So the next improvement is that, in fact, these torus, okay. This torus is really just a product of two circles. And so you might say, okay, maybe we can just keep this structure. So now we just take a product from two like linear maps, arbitrary linear maps. So first we take two just random sparse matrices, and these are, as we mentioned, you can show that these are good classical codes. And now we can take a tensor product of the two maps. So here we take a tensor product of two vector spaces that gives you f2 to the a tensor f2 to the c, and so on. So you have these vector spaces. And the linear maps, they, again, induce from like f and g.
Yeah, so it's just like you have matrices over A and C, and like one is working, like, and you do one operator on the row, one operator on the column. Right, that's like the.
Oh, you mean these?
Yeah, so we maybe say this explicitly.
You mean the linear maps here?
Yeah, like what?
I see.
Yeah, what?
Explicitly, let's see. Okay. So one way to think about these linear maps is that you can think of this map as having like C copies of F. Yeah, maybe I can draw something. So. Yeah, so linear maps can be like represented as some kind of graph. So there is so the linear map F between A and B, you can think of it as a graph between like vertices in A and vertices in B. And you can do the same thing for between C and D. Yeah, so really like the final thing, this tensor product, using this graphical language, you can think of it as you're taking two graphs and then do a Cartesian product. But that helps.
But what's x0 and x2?
Yeah, so this x0, this f2 to x0, this vector space is exactly this vector space, the same vector space. So x0, we can think of it as like a times c. So that's exactly the vertices, just like a times c. And x2, yeah, they correspond to b times d. And the vector space in between will be the direct sum of like the two on the opposite end.
So it's like B times D is the product of the edges of the two graphs. Like all the squares. And A times D and B times C, these are the horizontal edges and the vertical edges.
So it turns out we cannot think of it that way. Because that one would require us to take Tanner codes. Which will come later. For now we can, right.
In your metaphor of
Yes.
the graphs, it's exactly.
Yeah, so now it's the linear map that corresponds to the edges.
Like, I'm sorry, like, did I say something that was not correct? Like, if this is X, x0 is like the space of like A and C index matrices. You now have two maps, right? One that operates on the rows and the other that operates on the columns, right? And now x1 is just like apply these two maps separately and like write like a pair of matrices.
Yes.
And now like your second map is just
Then you apply the opposite one and you sum them again or something.
Yeah.
Yeah.
You apply the.
right. So
You
now,
start with the first thing.
yeah, so like the second map is what? You sum.
You apply like F tensor ID to one of the things and then IB tensor G to the other one, and then you get two things.
Now you have two things, right?
And then you
Because
just add them,
I mean,
add them together.
so is this like apparent in the drawing that you add them together? Or,
Okay, it might be a bit implicit, but this is what you're saying, right? Yes.
You see how it says f to the x1 is the direct sum of two things?
yes,
So x, yeah, so like x1 is the direct sum of these two.
no, that I understand, like, I don't understand how the map, how to read the map from x1 to x2 using this diagram.
Ah, okay,
Because I see that the diagram commutes, but like,
This is the way to make it.
yeah, you need to cycle.
no, to make the diagram commute, you don't need to do anything.
Or to
It
make,
is
to make
just
the kernel of,
diagram commutes, it's a beautiful diagram.
you need the image of delta zero to be in the kernel of delta one. That just makes it work, because if you start at the first thing, then you kind of
Yeah,
go and then get
that's-
the same thing back, so you add it,
Yeah.
you get zero.
Right. Okay, so maybe
No,
this would help. Yeah. Right, okay, so, okay, good, so it turns out this kind of process, like this kind of tensor, taking two tensor product of two linear maps, this is sort of well studied in mathematics, and so it turns out people know how to compute K directly from the data of the linear maps. So that's why we can get K linear to N from some kind of Kuhn's formula. But the distance is still square root. And this square root really comes from the issue that if you have a logical operator or like some code words inside your classical codes, then you can use that to convert into some logical operator on the qubit, like the quantum code side. And so really, yeah, since we already have the picture, what's saying is that like this classical code, it's also hidden inside your quantum code. And so if the previously the distance is d, then the new distance is also d. But now the issue is that now we have much more number of qubits. So previously it's like previously it's like you have like around an order d number of bits, but now you have an order d squared number of qubits. So that's where this kind of square root issue really comes from. So it really comes from this kind of product structure.
Just to maybe tell me if this is like taking you too far off, but all you really needed for this thing is the commutative diagram, right? Not the product structure.
Yes, it's really just a commutative diagram. That's right.
And like in a general commutative diagram, you may not necessarily get this like square root d, right? It really depends on like how x1 looks like. So it's
Yeah, so in general, you just need a commutative diagram. And but the issue is that how do I construct a nice commutative diagram? That's exactly the issue. And previously, the only way people know is to take whose product. But for some algebraic like topologists, they know that there are other ways. So in fact, that's exactly like the next construction people, like that's how people get this breakthrough, the square root barrier, which is by taking these fiber bundles. So these fiber bundles, they have the property that they locally look like a product, but globally they're not a product. So the fact that it's locally a product, it sort of helps with this kind of having this, like as you said, the structure. At the same time, the fact that globally it's not a product, it sort of just circumvents this previous barrier. And so let me just give an example. So on the left, it's just the usual product. So I have a base graph and a cycle in it. The product is just the usual Cartesian product. But then here we can consider a kind of a twisted product. So what I mean is that, okay, so these two edges is still the same thing. But then for the edge on the back, I sort of shifted sort of one step by the cycle direction. So this is known as the fiber bundle, and turns out in the paper, what they did is that they consider like a random kind of abelian lift. So they take a graph and then consider a random abelian lift, and that already surpassed the square root barrier. Yeah, so that's really the idea.
So these are all existence results, like can you decode any of these things efficiently?
Oh, yes, you can.
Okay.
You can decode these things. So, right, yeah, and in fact, this kind of twisted product structures also appear in some later results. So, for the next few minutes, I'll talk about this, like how do you get this kind of result? And so it's based on a different kind of twisted object, and we'll call this the LeftRight K Complex. So it actually has several names, such as like lifted product, balanced product, but they're really all the same thing. So what we do here is we take a non-abelian group and then two sets of generators of size delta. So delta is some constant, while G, it will just, it's a family, it will grow to infinity. And what we do is to construct something similar to a Cayley graph. So we have 4 copies of G. And then we will connect the edges. So the horizontal edge would be generated by A and the vertical by B. And so in particular, G would connect to AG and also GB vertically. What's interesting is that the left and right action, they commutes. And so what happens that AG and GB, they'll both be connected to AGB. Yeah. And what that means is that now you have these additional property like the square. And so together, so if you look back at this picture, what you should have in mind is that it's a bunch of squares and then they're glued along the edges. Right. And so this structure do have this property. So if you look at it, it doesn't have globally, it doesn't have a product structure, but locally it does have one. So if you look at the structure around a vertex G over here, it's connected to AG, A prime G, like different things, and then GB, different things. And you can see that for every pair, you can construct another vertex on the bottom right. So really the structure is like a product of a star-like graph. So 2 stars, one over here and one over here.
Sorry if this.
Yeah.
Will you get into like it would be useful if you could write out explicitly how you take a group G, generators A and B, and you get a code out of it. Like that would be very
Let's see.
If this is hard, then
Even just a code. Just any code.
what code do you get from us? Like A, B, and G, what code do you get explicitly?
Like what kind of G do I have to take, for example?
No. Just fix G, fix A, fix B.
Yes.
What is the resulting like matrices H and like HX and HZ?
Okay, we want to look at the explicit matrix.
Yes.
Like 0, 1, 0, 1.
Well,
Well, I guess
or the linear maps. Like,
one answer is
Uh-huh.
you also need an extra data, which is the local codes, which you didn't yet say.
oh, okay.
But if you want to ignore that, you can just look at the matrix that's the incidence matrix that says for every edge which squares it touches. And you get an edge versus squares matrix, and that would be a nice code, except it doesn't work. But it's like a good start.
Okay.
Right. So for example, just starting from this complex, there are already several ways you can generate the chain complex. One way is we can set the top left to be the X check, just like before. Like the commuting structure that was shown in one of the previous samples. So we put the qubits on these 2 diagonal parts, the X check on the top left, and then Z check on the bottom right. So that's one way to construct a chain complex just from this geometrical structure. And the other one is, of course, the one Irid just mentioned, which is by taking the geometry, like the geometry side. So we map from the vertices to the edges to the faces. That's another way.
No, I don't understand. No, and it's, sorry, I need to be more specific. Like, when you say you put the qubits, you mean you put like, this is just the strings that you're going to do like X and Z checks on them?
Mhm.
Okay, and then like, when you say you put the X checks on Z, or the X check on like the top left,
Uh-huh.
this, like what does this mean?
Yes. Okay, let me draw it over here. Yeah, so here are a bunch of vertices, and when I say I put like a X check on these vertices, I mean that so here are the qubits that form my quantum code, and whenever this vertex, right, so if this vertex touches these qubits, then like, yeah, this X check would check on these
So like
qubits.
you're putting linear constraints on the neighborhood of every
Right.
like blue vertex here. So that's
Yeah,
I
so
think it might be good to separate the physics from the combinatorics. So you can think of all this work as you're trying to construct a chain complex. And then, sometimes you can say, well, the chain complex is like X checks to qubits to Z checks, but these are just names, right? So it's just a three-term chain complex where you call the first space X checks and the last space Z checks and the middle space qubits. I don't know if you were asking about the physics or about the combinatorial.
No, I was just as a follow-up to Jan's question, to understand what's going to go on here with the actual design code, like using this product. Like, I don't yet understand like where the product structure comes in, but like maybe I'll ask about this later.
Mhm. Okay.
Was the product structure like help make the image of the first map be?
Yeah, so the product structure is used to satisfy this HX, like to satisfy this HX transpose times H, this condition.
Like our entire goal right now is to build these two matrices HX and HZ so that they compose to zero.
Yes. Right, okay, so now we have a geometrical object that has this kind of twisted property, so at least we have a chance to break this square root. But from here, we don't have a code yet, so now the next question is how do we build a code out of it? And that's where we'll enter this discussion on Tanner code. So let me first describe the how you define the Tanner code in 1D. So it's just a traditional expander code. So first you will take an undirected graph. And then you'll put the bits on the edges. So now the word like C would be inside some F2 to the E. Okay. And now we say for C to be a code word, we need to satisfy some constraint. And the constraint is that for each vertex, if you look at the value along the neighboring edges, it has to be inside some local code. So in this example, around this vertex, you have value 1, 1, 1, and you want those, and this forms a vector, you want this vector to be inside some code. Right, and yeah, okay, so that's the definition. So that's how you can construct these Tanner codes. So given a graph and the local codes, that would give you like a global code. And sometimes later on, it'll be useful sometimes to, instead of looking at the parity-check matrix of the local code, which we'll denote as an H. And another helpful thing to have in mind is that you can think of this check as a large check, as like a big check. And secretly, it's actually consists of many small checks, small actual parity checks. And these parity checks comes directly from the local code. So in this example, what's going on is that you can think of this large check consists of two small checks. This first check would check like these first two values to be the same. And the second parity check would check that the second and the third bits are the same. Okay. So, all right, so we will next now generalize this to like the 2D case. So the goal is again to construct some chain complex. And we'll start with some 2D complex. So let's just say the square complex that we constructed. What we'll do next is to attach some local coefficients. So for the face, we again just put an F2, but for the edge, similar to the check that we just saw previously, we would sort of like put something more into it. So in this case, it's like a vector. We'll put a vector for each edge. And then for each vertex, we will put like a matrix valued object there. And so more explicitly, what's going on is that now this first vector space, it would be this F2 to the M1 times M2 to the power of V. So in other words, you can think of it as a function where a function on the vertices where each vertex has a value inside like F2 to the M1 times M2. Okay. All right. And so now we can build the linear maps between them. So these linear maps again would come from some information of the local linear maps. So, right, so here this H1, it's a map from M1 to delta. So this H1 tensor I will map this matrix into a larger matrix. So delta times M2. So what happens is that, okay, this vertex, it's connected to delta many edges. So So what's going on is that this delta many columns, it will be sort of distributed along to these delta edges. So that's how you can build this delta zero map. So let me just say it again. So you have some function value on the vertices. Now we want to get some function value on the edges. And what you can do is you can first apply this H1 to form some matrix and then distribute it. So that defines the map. Okay, so so in this, so now we want to check that it's a chain complex, but really to check that this globally is a chain complex, all you need to do is you check that locally it's a chain complex, like the constraints are satisfied locally. And essentially this local part is satisfied because we really just take the tensor product of two maps, H1 and H2. Okay. So yeah, that's how you can apply tenor codes even in the 2D context. And that's exactly the construction for these good qLDPC codes. So essentially what they say is that there exists some suitable local codes with parity-check matrices H1, H2, such that the corresponding tenor code on these LeftRight K complex has these optimal parameters. And so one thing I didn't tell you is that these K complex, they have to have some spectral expansion properties. And these can be satisfied, for example, using these LPS like Ramanujan maps. So right. And some related construction will also discover later on. So one thing I haven't really tell you is like, what is this like local condition? So maybe I'll say a few words on that. So, right, sorry, actually, let me see. So I think I'll definitely run over time. So how should we?
Yeah, okay, we can see. I mean, what do you want to skip the local condition or?
Yeah, yeah, let me skip this part. Let me actually skip this part. Yeah, so and let me just say that in high dimensional expander, there is a notion called this Cobound expansion. So it's really a very natural notion when you want to generalize Cheeger kind of constant to this chain complex setting. And turns out this local condition can be kind of phrased in kind of this kind of language. But turns out I'm slightly like ignoring some detail. Yeah, but I won't go into that. But the point is that this local condition is also very natural, and it can be viewed as a generalization of the notion of distance. Right. Yeah. So just to summarize, we can combine the K complex and this kind of local codes to obtain these good qLDPC codes.
Okay, actually, let me stop you here.
Okay.
The picture you have here on the bottom right, go to the next slide.
Oh, this slide.
Yeah, that's what your town was, I think, talking about, right? Where you have this commuting diagram and the black guys are like the middle layer on your. No?
I thought that was what you said. Yeah, okay.
All right.
No.
Yeah. I feel like it would have been good to describe the quantum code with this in mind before going to the more complicated construction you showed now, which is basically taking this and kind of putting it many local copies of this thing all over your graph. And that's how you get the global good.
Okay. Right. I'll sketch some like say a few words on how we can prove this kind of distance results. So so I mentioned that there were actually like about 3 papers that tried to just prove pretty much the same thing with slight difference in the construction, but the proof techniques sort of improve over time. And the reason is that in the really first paper by Pantellev and Kolachev, they didn't have this object, like they didn't have this local code with this very nice Cobound expansion property. So their proof is more involved. But now, since we have these kind of construction, the proof is much more streamlined, and it's pretty much like the classical proof for the expander codes. Right. So so as we sort of mentioned, in quantum you have 2 kind of distance, dx and dz, and they correspond to like distance in different directions. So for the forward direction, the proof really follows from the spectral expansion of your graph together with the Cobound expansion of your local code. Okay, and you can sort of compare with this kind of expression in the expander code. So in the traditional expander code, people know that if your distance of the local code is greater than your spectral expansion of your graph, then overall the global code is good. So in our context, we can also get a somewhat similar expression. So on the left, it's all about the property of your local code. And on the right, it's the property of your graph. And what about the reverse direction? So it's kind of interesting. So the way we can show the reverse direction is by reducing this case to the previous case. So somehow we have a way to reduce the homology question to the cohomology question. And so this is discovered early on, but recently, like we finally realized that it's actually a kind of Poincare duality. So there's a very nice story behind why this reduction just works. Okay, so that's really the 2D case. So the original plan is that later on we'll talk about the quantum locally testable codes and also codes with transversal links. Yes.
So I was asking before, so the distances of the both are related? If one has good distance, the other has good distance?
Oh, in general, you won't have this property. In general, it's like two different questions.
So what makes this, you're saying you can reduce one to the other?
Yeah.
Why?
Yeah. So I don't reduce. So okay, when I do the reduction, actually the local code change. So if the original code, the global code has local code CA and CB, after passing through this reduction, it becomes CA perp and CB perp. So it's a slightly different code, but the proof technique it's this, it has the same structure. So the proof is the same. Yeah. So for quantum, we actually need to condition both on the code, like local codes, we need it to both on the code, but also its dual, like the dual code, which sometimes make things more challenging. Yeah. Okay. All right. Yeah. So the original plan is that later on I'll talk about the quantum locally testable code case and also the case with transversal gates. But I think because of time, I think I'll just talk about one of them. Let me talk about the one with transversal gates, let's say. Yeah. Let me just say one thing, which is, that, so it turns out to think about quantum locally testable codes, you can compare with some codes within a similar family. So there is the classical LDPC codes and the quantum LDPC code we just discussed. But turns out around the same time, there is also this breakthrough on classical locally testable codes. And the breakthrough, the key idea is that instead of just looking at the bits and the checks, we also look at the relation between these checks. And just by adding a linear map, we can sort of construct good classical locally testable codes. And so here you can apply a similar idea to quantum locally testable codes by including the relation between X check and Z check. And so now you can, now you can reduce every question to just question about constructing chain complex. But now we want to have like 4 linear maps. And so the construction is somewhat similar, but now you generalize into a 4-dimension. So you build a Tanner code on the 4D cubical complex. Okay, so that's all I'll say for the quantum locally testable codes. And turns out our proof is like, it's already streamlined, so that can be generalized rather straightforwardly to the 4D case. Okay, so now I'll talk about codes with transversal gates. So let me just say a few words on the motivation. Right. So let me first describe the idea. So, right, this part would involve a bit of a physics, but anyway. So what we want to do is to encode k qubits into n qubits using quantum LDPC codes. But what we want here is that when we apply some logical operation on the quantum state, so meaning that it's an operation that still maps code words to code words, you want such operation to be implemented in some like constant depth on your physical qubits. So you want to have some relation between the logical operation and some kind of physical operation. And let me illustrate it using a picture. So at time 0, you have a k qubit quantum states, which is now encoded into n physical qubits. what we want is that we want to apply some kind of gates on the classical bits, such that at time one, you somehow get some operation on logical, also on logical qubits. So this T psi, it's again still a code word. So it's still in your code space, but it's, yeah, there's some operation on it. And that's where the computation comes from, yeah. So here is the case without error. You get a clean object at the end, but in general, there might be some error in your circuit. So here, here I'm drawing quantum circuits. So in general, there will be some circuits, so your end state would be noisy. What we can do is you can apply an error correction, and at the end you will get a clean state. And here we really want this circuit to be implemented in constant depth, because otherwise, if it takes a long time, then the error will sort of accumulates. Because in between we don't do error correction, so the error will accumulates. And if there are too many errors, then no error correction could sort of help you. So.
Okay, so you're saying this is practical. Is there any complexity theory application like yes and all this?
Right. So someone like a PCP, I would say. Okay. So in a PCP, in a like real world context, these errors are sort of like random noise, like random error. But in like a more PCP context, you can think of it as like adversarial kind of noise model. And it seems like there's some relation between the two. Okay. Yes. Okay. So this is the context where we care about these transversal gates. And one of the gates that we'll care about here is the CZZ gates. So a CZZ gates is a quantum gate that acts on 3 qubits. And you can think of it as an analog of the AND gate. So linear code, it's very good at doing like plus, like you can do like kind of plus operations. But for multiplication operation, you need something else, which is exactly the AND gates. So AND gates would map AB to A times B. But for quantum gates, these are reversible. So it's better to think of it as ABC maps to AB and then C plus AB. Okay, so this is now reversible. But actually in quantum, you have this, you can allow phases. So actually it's even better to think of it in this way. So you map ABC to ABC, but then there's a phase change, which is minus to the power of ABC. So effectively what's doing is that it will map 111 to minus 111, and everything else it would just stay the same.
Why do you need the third qubit then?
Oh.
The phase. Why can't you just do AB to minus AB?
Oh, like AB to minus AB. So it turns out, when you think more about it, it turns out it doesn't do computation. It just do plus. Like, turns out it's secretly. So in quantum, there's this notion of like Clifford hierarchy, and if you only have AB, then it is within a smaller hierarchy that doesn't cover the universal gate set. But once you have this additional like ABC, then it does cover the universal gate set. Okay. Right. And so more generally, actually, this also, you can also generalize this to like larger field size. But overall, the point is that CZZ really just acts on 2 qubits and then it changes some things. And later on, we want to use CZZ to build some logical operation. And to talk about that, let me just like review some fact about logical operators. So previously, we say that these logical operators have to act in the host, act inside the code space. And the code space is sort of described by these equivalence classes. So it's like X inside your cycles, but it's equivalent up to like adding some boundary. Okay. Right. So in particular, the Pauli operator, when you use this kind of language, you can think of it as a function that maps y to y plus x. And what's important is that this function, we want it to be defined on the cohomology classes. We want it to be defined on the cohomology classes. And so what it means is that if y is inside z, then the image is also inside z. So that's one condition. But another thing is that if 2 things are in the same classes, so for example, y plus b and then y, then their image should also be inside the same class. So that means their difference should also be inside some b, inside some boundary. Right. And so the summary here is that for for something to be a logical operator, meaning that they map code words to code words, the corresponding function should be defined on this Cobound classes. So here I'm just kind of doing a translation from the quantum physics world into some kind of a combinatorial requirement. Okay, and now we are ready to talk about the logical CZ operation. So again, CZ is something that acts on three things, and I just changed the phase. So now we want something to act on bit strings. So that means we'll want to map XYZ into XYZ, but with a phase. And the phase is determined by some function. In this case, a trilinear function f. So that's, yeah, so you can think of these three things as being living on like three quantum codes, Okay, so we have this function. So now we want this operation to be acting on the code space. So equivalently, what's saying is that we want f to be defined on the cohomology classes. So the condition we want is of this form, which is that f x plus a, y plus b, z plus c, it should be equal to f of xyz for xyz inside the cycle, and then abc inside the boundary. So that's one condition we want, but at the same time, we also want like this transversal property. So what does it correspond to? So that's saying that we want this operator to be implemented in the short depth. So one way to implement such operation is to say, okay, when f of ei, ej, ek is equals to 1, then we would apply some CZZ on the ith qubits, ith and kth qubits. So it turns out if you do this for for every entry, you will get this operation. Right. And now we want this to be implemented in a short depth. So turns out what that means is same as saying like how many non-zero entries there are inside this function when you restrict the first variable to ei. So in other words, let me just say in a different way. So this function, you can think of it as a tensor, like a n by n tensor. And the values are in F2. And this condition is saying that we take the ith layer, we only want to see like constantly many non-zero entries. And so in other words, this is just saying that F should be something sparse. So really the goal here is to find some sparse trilinear function, such as defined on the cohomology classes. And yeah, so for some of you, this might look familiar again, where these kind of things can be constructed from the cup product or the intersection number in algebraic topology. So yeah, so that's really the key point. And let me give you an example, and then maybe we'll like stop there. So let me give you so previously it's kind of abstract. So let's look at an example. So it's sort of known that 3D Tor code, they support these CZZ gates. And what are these 3D Tor code? They're really just like 3D toruses. And for a 3D torus, we know that it has like 3 non-trivial homology. So that corresponds to the 3 planes. So these 3 planes, they don't contract. They cannot be contracted. Okay, and these things, they would correspond to some X logical operators. So what's known is that one can bring these 3 codes together and then apply some local CZ operation, so infinite depth. And what happens at the end is that it effectively applies a CZZ on the logical qubits. And why does it have such a property? It really comes from some topological feature. So the topological feature is that you have 3 planes. These 3 planes intersect at exactly 1 point. And if you deform these planes, the number of sections is still the same. So it has this topological nature. And really the lesson is that, okay, you can start from these triple intersection, and that gives you a way to build these trilinear function, and that induces these transversal CZ gates. Okay. Yeah, so in fact, once you know this fact, you can see that this naturally generalizes into all dimensions. So these are like 2 intersection, 3 intersection, and like 4 things intersecting, and yeah, you can generalize it. And this was also somewhat observed in, actually, let me say an interesting thing, which is, so interestingly, previously in quantum locally testable codes, we want to go to a higher dimension because we want to get relation check. So now we have another reason to go to higher dimension, which is to get these triple intersections. Yeah, so it turns out if you just take this 2D version, which turns out it doesn't give you universal gate set. You really need to go to 3D. Okay, and in fact, some similar fact was observed in some other papers. But one thing we can do more is that we can extend these ideas into the context of these Tanner code I just described. So let me just quickly say what's going on. So what we did is that we can interpret the logical operators in your quantum code as these plane configurations. And the local codes can actually be interpreted as how these plane ends on the boundary. So yeah, okay. And once we have this interpretation, we can define our function f to be the triple intersection between these surface representations. And from there, one can ask, okay, how can I make sure that f is kind of a topological invariant? Yeah, so what I mean is that these surfaces you can sort of move slightly along the boundary, but you want to make sure that f is still an invariant. And it turns out if you work out the detail, it corresponds to some local constraints on the local codes. And this actually is very similar to the classical condition of like multiplicity codes. So now once you have it, the corresponding CZ operator would indeed map codes word to codes. Okay. Any questions? Okay, so let me see. So that's how we can so this is one of the instances that we can generate from those understandings. So what we do is that we can take three classical qLTPC codes with the local codes, with the property of the local codes I just described, and then you just take a tensor product of the three. So together they would give you like a chain complex with three linear maps, and then now we put them in the correct way such that the X logical operator, they correspond to these 2D surfaces. So that's pretty much the construction. There is actually a funny challenge in this problem.
What is the requirement on the local codes? And you say,
I see.
take three classical LDPC codes with some properties, so what is
Yes.
the code that satisfies?
Yes. So let me say the property. So the property is that you take three code words from your code, you take their entry-wise product, and you add up the results, and you want it to be 0. So this is actually quite similar to the multiplicity property. So usually in the classical setting, it's written as C1 like dot C2 is contained inside C3. But another way to write it is that C1 dot C2 dot C3, it's like equal to 0. So something like within the parity-check matrix. C3 parity. So that's sort of a relation here. Okay. All right, so so previously I was going to talk about a funny challenge here, which is
But they're mostly out of time.
Let's see. Should I talk about this?
Maybe try to summarize it.
Okay.
Maybe say that you're here all week, and so you can more informal conversations.
Okay, sounds good. Yeah, I'll just pose an interesting question here, which is somehow in this context we want to lower bound the code rate, but the traditional way of bounding is not so easy. And so what we need is actually somehow we encounter this kind of question, which is we want to embed a graph inside some vector space. So here on the left, we see a graph with these vertex and edges. So the vertex now want to map into some line, and then the edge want to map it to some point. And so that means on the left, we have two vertex with the edge between them that will correspond to two lines that intersect at a point. And the goal is sort of like want to embed, like, for example, Ramanujan graph into some vector space. And we don't exactly know how to do it very effectively, things like that. So that's one of the challenge. All right, let me just yeah, let me just conclude, which is, yeah, so I sort of mentioned that these quantum LDPC code, they're somewhat solved, and there's still these open question on BCP, and in between there is some intermediate question, which we have made some kind of partial progress. And really, yeah, okay, right, and some further directions. So one is that currently our code parameter is not optimal yet, and one of the challenges that that these two conditions somewhat don't match that well. So what I mean is that this local code constraint here, it's satisfied by the Reed-Solomon code, but turns out Reed-Solomon code do not satisfy the first property. So that means we maybe need to like consider a larger family of local codes with this property, or maybe we need a better like proof technique, like a tighter proof technique. Yeah, and the second question is the one I just talked about, which is to improve the rate, we might want to embed these. We want to like understand how to embed like Ramanujan graph into these very well structured algebraic structure. And it seems possible because these Ramanujan graph do come from rather like arithmetic structure. So maybe it's possible, but it's not that studied, so we don't know how to do it yet. Okay, so that's everything.
Okay, thank you very much. Any questions?
Do we probably know that Reed-Solomon codes don't satisfy A?
Let's see. So if we just take the simplest Reed-Solomon code, like we evaluate at every point, then indeed there are counterexamples. But you can consider more complicated Reed-Solomon codes, like we just sample on some places. For those, I'm not. Yeah, maybe it's not an issue. Yeah.
Well, Reed-Solomon doesn't have local parity checks.
Right, but these are also for local codes.
For local codes, yeah, these are for local codes.
For the local code.
So it's fine.
Okay. Yeah. Any more questions? Okay, all right, thanks.